There's a streak of light in a Hubble Space Telescope image that, for years, nobody could fully explain. It's perfectly straight. It stretches roughly 200,000 light years, which is longer than our entire Milky Way galaxy stretched end to end. And it's made almost entirely of young blue newborn N stars, arranged in a line so precise it looks less like something nature would produce and more like a scratch left by a cosmic ruler. When astronomers first spotted it, they genuinely weren't sure what they were looking at. It took years of follow-up observations, a fresh set of instruments on the James Webb Space Telescope, and a lot of careful, patient science to finally settle the question. And the answer, when it came, turned out to be stranger than almost anyone expected. At the leading edge of that line of stars is a supermassive black hole, tearing through intergalactic space at nearly 1,000 kilometers a second, having apparently been ejected from its home galaxy entirely. It's the first confirmed case of something astronomers have theorized about for decades but never actually caught in the act: a runaway supermassive black hole. It's also worth taking a moment to appreciate just how strange it is that we're able to see a runaway black hole at all, given that black holes themselves emit no light. RBH1 doesn't announce its presence the way an actively feeding supermassive black hole would, with a brilliant glowing accretion disk or blazing jets visible across multiple wavelengths, the kind of signature astronomers usually rely on to spot black holes at cosmological distances in the first place. RBH1, as far as current observations show, isn't actively feeding on nearby material in any dramatic way. It's essentially dark, a genuinely invisible object, detectable only through its gravitational and mechanical effects on its surroundings, the bow shock it drives into the gas ahead of it, and the trail of star formation it leaves behind. That's precisely why this kind of object is so difficult to find in the first place, and why it took a fortunate, almost accidental spotting of an oddly straight streak in archival Hubble imagery rather than any deliberate, targeted search, to bring RBH1 to astronomers' attention at all. Most of what we know about supermassive black holes across the universe comes from studying them while they're actively feeding, glowing brightly enough to be picked out against the darkness of space. A quiet, non-feeding black hole in the middle of nowhere, between galaxies, with nothing but a faint gas disturbance to mark its passage, is close to the hardest detect, which makes the fact that astronomers caught one at all feel almost like a stroke of genuine luck layered on top of genuine scientific persistence. Let's start at the beginning, because the discovery itself has a genuinely interesting origin story. Back in 2023, a team led by Yale University astronomer Peter Van Dokkum was working with Hubble data, studying a distant galaxy cataloged as RCP-28, sitting at a redshift of roughly 0.96, meaning its light has been traveling toward us for about 7.5 billion years. While examining the imagery, the team noticed something odd sitting right beside the galaxy, an unusually straight, narrow streak of light. At first, that kind of feature is exactly the sort of thing that gets dismissed as a data artifact, a scratch on the detector, a cosmic ray hit, something you clean up and move past without a second thought. But this streak persisted across multiple imaging filters, which meant it was real. Once the team confirmed that, they realized they were looking at something genuinely unprecedented. Van Dokkum himself put it plainly at the time: nothing quite like this had ever been observed anywhere in the universe. Here's where the numbers start to get genuinely strange. The streak, later given the designation RBH1 for runaway black hole 1, stretches about 62 kiloparsecs, which converts to roughly 200,000 light years, nearly double the diameter of our own galaxy. And it isn't just a faint smear of unresolved light either. Spectroscopic follow-up, first from the Keck Observatory in Hawaii and later from JWST, showed that the streak is composed of genuinely young blue stars, hot newborns rather than an older stellar population, arranged along the entire length of the feature. That single detail turned out to be crucial to ruling out one of the earliest and most obvious explanations for what this thing actually was. The Discovery team's first working hypothesis was that this might simply be a very thin, edge-on galaxy, one so narrow and precisely aligned that we happen to be viewing it exactly side-on, seeing only its slender profile rather than its full disk. It's not an unreasonable first-guess edge-on disk. Galaxies really can look remarkably thin and streak-like from certain angles, but the stellar population data ruled that idea out fairly quickly. A normal galaxy, even a small one, contains stars of many different ages and colors, the accumulated stellar history of a system that's been forming stars for billions of years. What the team found instead was a population that was almost uniformly young and blue, exactly the signature you'd expect from a single, relatively recent burst of star formation rather than an entire galactic disk's worth of stellar history. On top of that, very tip of the streak, The end farthest from the parent galaxy showed an extremely strong signature of doubly ionized oxygen, a spectral fingerprint that only shows up in genuinely extreme high-energy environments, the kind of environment you don't typically find sitting quietly at the edge of an ordinary galactic disk. The second hypothesis the team seriously considered was jet-induced star formation, essentially the idea that a narrow jet of material blasting out from an active galactic nucleus in the nearby galaxy might be plowing into and compressing surrounding gas as it traveled, triggering a wave of star formation along its path. This isn't a hypothetical mechanism. It's something astronomers have directly observed elsewhere in the universe, most notably in an object called Minkowski's object near the galaxy NGC 541, and in the much closer, well-studied radio galaxy Centaurus A, where jets from a central black hole really have triggered pockets of star formation in gas clouds they've slammed into. It was a genuinely reasonable explanation to test, but the shape of RBH1's streak argued against it. A jet-triggered star formation trail should get wider as you move further from its source, because the jet itself is spreading and interacting with more surrounding gas the further it travels. RBH1's streak does the opposite. It's narrowest at its tip, the point farthest from the parent galaxy, and the strongest evidence of shock interaction also. Shows up at that same distant tip, rather than closest to the galaxy where a jet's point of origin would be. That's essentially the reverse of what jet-induced star formation should look like, and it was enough to push the explanation off the table. With those two more conventional explanations ruled out, the team was left with something considerably more exotic. The idea that this streak might be the wake of a runaway supermassive black hole, physically plowing through intergalactic gas and leaving a trail of triggered star formation behind it as it went. The theoretical groundwork for this idea actually goes back decades. Back in 1983, physicist Michael Fitchett showed mathematically that when two black holes merge, the process can release gravitational waves asymmetrically, and that asymmetry can impart a powerful recoil kick to the newly merged black hole, potentially sending it flying at speeds high enough to escape its host galaxy entirely. It's a real, well-established prediction of general relativity and black hole merger physics. What nobody had ever managed to do in more than 40 years since that prediction was actually catch one of these ejected black holes in the act, with clear, unambiguous observational evidence. That's where the story picked back up in December of 2025, when Van Dokkum's team returned to this object, this time with access to the James Webb Space Telescope's much sharper resolution and spectroscopic capability. Using JWST's near-infrared NIR spec instrument in integral field unit mode, essentially a tool that captures both an image and a full spectrum for every point across a small patch of sky simultaneously, the team was able to map out the velocity structure of the gas at the tip of the streak in far greater detail than Hubble or Ground based telescopes had allowed before. What they found was about as close to a smoking gun as observational astrophysics gets. There was a sharp, sudden jump in gas velocity right at the tip of the feature, on the order of several hundred kilometers per second, over a distance of just about a kiloparsec, the kind of abrupt, localized velocity discontinuity that essentially only happens when something massive and compact is moving supersonically through a surrounding medium, compressing and heating the gas directly, ahead of it into what's called a bow shock. Think of the wave that piles up in front of a boat's hull as it cuts through water, except here the water is the extremely thin, diffuse gas that fills the space around and between galaxies, called the circumgalactic medium, and the boat is an object with the mass of roughly 10 million suns. The research team themselves described the evidence for this supersonic bow shock as, in their own words, very strong, bordering on overwhelming. That confirmation is genuinely significant on its own terms. This is the first time astronomers have gathered direct observational evidence, rather than just theoretical prediction or indirect circumstantial hints, that a supermassive black hole really can be flung entirely out of its host galaxy and go careening through intergalactic space. But it raises an obvious and slightly uncomfortable question, one that cuts against everything most people think they know about black holes. We tend to picture black holes as engines of destruction, consuming stars, tearing apart anything that strays too close, growing by devouring their surroundings. How is it that this one is apparently creating new stars in its wake instead? The answer comes down to what's actually happening in the space directly behind the black hole as it moves. As RBH1 barrels through the circumgalactic medium, its passage doesn't just create a bow shock out front, it also stirs up and compresses gas that trails along behind it. That gas cools as it moves away from the immediate shock front, and as it cools and mixes with other surrounding material, dense clumps within it can collapse under their own gravity. Exactly the process that triggers star formation anywhere else in the universe. In effect, the black hole isn't directly manufacturing stars through any exotic mechanism. It's disturbing and compressing enough interstellar gas along its path that ordinary star formation, physics takes over and does the rest. It's a genuinely elegant, if slightly ironic picture, one of the universe's most destructive objects, moving through space in a state of complete cosmic exile, inadvertently seeding a 200,000 light-year trail of stellar nurseries in its wake. So, where did RBH-1 actually come from, and what sent it flying in the first place? This is where you have to be careful, because a fair amount of coverage of this discovery, including some fairly prominent retellings online, has gotten this next part wrong, and it's worth setting the record straight. You may have seen this object linked to a strange symmetrical two-galaxy system nicknamed the Cosmic Owl, sometimes also called the Infinity Galaxy, because of its owl-like appearance formed by two ring galaxies colliding almost head-on. It's a genuinely fascinating object in its own right, a system so rare that ring galaxies alone make up something like 1/100th of 1% of all known galaxies, meaning the odds of two of them existing close enough together to collide, let alone actually colliding nearly head-on, are vanishingly small. The Cosmic Owl contains three separate active supermassive black holes, two sitting at the eyes, cores of the merging ring galaxies, forming the eyes, and a third sitting in the gas-rich beak region between them, where researchers have found evidence that this third black hole most likely formed in place, directly within that dense collision-triggered gas cloud, rather than having been ejected from either parent galaxy. But here's the correction worth making clearly. RBH-1, the actual runaway black hole with a confirmed bow shock and the 200,000 light-year stellar wake, is not part of the Cosmic Owl system at all. It's an entirely separate object, sitting beside the distant galaxy RCP-28, a completely different system from the Cosmic Owl. The confusion appears to stem from the fact that Peter van Dokkum and several of the same collaborators authored papers on both objects around the same time, and both involve the general theme of displaced or unusually positioned supermassive black holes, which made it easy for secondary reporting to blur the two together into a single narrative. They're related in subject matter and shared authorship, but they are not the same discovery, and RBH-1's actual origin story doesn't involve the Cosmic Owl's dramatic ring galaxy collision at all. So what does explain RBH-1's origin, if not that specific system? The honest answer is that the team's confidence here rests on general physical reasoning about how black holes get ejected from galaxies, combined with measurements of RBH-1's mass and velocity, rather than a direct observational trace back to a specific ancestral collision event, the way the earlier, since-corrected framing implied. There are two theoretically viable mechanisms that can send a supermassive black hole flying fast enough to escape its host galaxy entirely. The first is a three-body gravitational interaction. When two galaxies merge, their central black holes can spiral together into a long-lived binary system that can persist for billions of years. And if a third supermassive black hole later wanders close enough to that binary during a subsequent merger, the resulting three-body interaction can violently eject the lowest mass member of the trio out of the galactic core entirely. The second mechanism is gravitational wave recoil from an actual black hole merger, the same physics Michael Fitchett described mathematically back in 1983, when two black holes finally merge into one. If the merger isn't perfectly symmetric, the newly combined black hole can be given an enormous kick from the asymmetric release of gravitational waves, sending it rocketing away from the galactic center. Distinguishing between these two scenarios for RBH-1 came down largely to its measured mass. In a three-body ejection, physics strongly favors kicking out the least massive of the three interacting black holes, since it's the lightest object that gets flung away while the more massive pair settles into a stable binary. But RBH-1 was measured to be substantial, at least 10 million times the mass of our Sun, which makes it a poor fit for being the lightweight loser in a three-bodies scramble. That mass profile instead points much more strongly toward the gravitational wave recoil scenario, where the object that gets ejected is the newly merged combined black hole itself, meaning RBH-1 likely represents the product of an earlier merger between two roughly comparable supermassive black holes at the heart of its own now abandoned host galaxy, kicked out by the asymmetric gravitational wave burst released the moment those two objects became one. It's worth being precise about how well established this conclusion is. The research team themselves described this gravitational wave recoil origin as the best supported explanation given the available evidence, built from theoretical modeling and mass measurements rather than a direct gravitational wave detection of the original merger event itself, which would have happened roughly 8 to 9 billion years ago, long before any gravitational wave observatory existed to record it. What makes RBH-1's confirmation such a genuinely important moment in astrophysics isn't just that it validates a decades-old theoretical prediction, though that alone is significant. It's that the discovery came with an unexpected bonus finding nobody had specifically predicted in advance. Earlier simulations of runaway black holes had suggested their wakes might glow faintly as disturbed gas settled and cooled, but relatively few researchers had anticipated that those wakes could become genuine active stellar nurseries capable of producing millions of new stars along a track spanning hundreds of thousands of light years. That's a real update to how astronomers think about the relationship between galaxy mergers, black hole dynamics, and star formation across the broader universe. And once you accept that this kind of ejection genuinely happens, at least occasionally, it raises an obvious follow-up question. How common is it? Galaxy mergers themselves are not rare events over cosmic history. They're a routine part of how galaxies grow and evolve over billions of years, which means the black hole binaries that eventually produce mergers and the occasional three-body encounters that can eject a black hole. Outright, should also be happening with some regularity across the observable universe. Before RBH1's confirmation, astronomers had already flagged a handful of other tantalizing candidates worth investigating further. One example is a spiral galaxy roughly 228 million light-years away, cataloged as JZ437Plot2456, whose central black hole, at around 3 million solar masses, appears to be moving at a noticeably different velocity than the rest of its host galaxy, a potential sign that it's drifting rather than sitting anchored at the galactic center, the way supermassive black holes normally do. Another intriguing case involves the central galaxy of the Hubble 2261 cluster, which by all rights should host one of the largest supermassive black holes anywhere in the observable universe, with mass estimates ranging as high as tens of billions of solar masses, and yet no clear evidence of any central black hole has actually been detected there at all. Researchers investigating that gap have floated the same basic mechanism confirmed in RBH1's case, gravitational recoil from a black hole merger, as one plausible explanation for why Abell 2261's expected monster black hole appears to simply be missing from where it should be. For now, RBH1 remains the only case where astronomers have assembled genuinely direct, conclusive observational proof rather than suggestive circumstantial evidence, and finding it required an unusual combination of fortunate viewing geometry, painstaking follow-up spectroscopy across 3 separate observatories, and years of patient work ruling out every more conventional explanation first. That's part of why it took so long to confirm in the first place. These features are inherently faint, thin, and easy to miss or misattribute unless you happen to be looking in exactly the right place with exactly the right instruments. That's likely about to change. Upcoming wide-field survey missions, including the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, are designed to scan enormous swaths of sky at Hubble-level image clarity, and combined with modern machine learning tools specifically, built to flag unusual linear features automatically. Rather than relying on a human researcher happening to notice one by eye, astronomers expect to move from a single confirmed runaway supermassive black hole to what could eventually become an entire cataloged population of them. It's worth taking a moment to appreciate just how difficult a measurement this actually was, because the technical achievement here is arguably as impressive as the discovery itself. RBH1 sits at a distance where its light has been traveling for roughly 7.5 to nearly 9 billion years, depending on which distance estimate in the literature you're looking at, meaning astronomers weren't observing some nearby, easily resolved structure. They were trying to measure a subtle, localized shift in gas velocity across a feature so distant that it appears as little more than a faint smear even through Hubble's optics. What made the JWST measurement possible at all came down to a fortunate coincidence of geometry. The entire structure, the black hole, its bow shock, and the trailing wake of young stars behind it happens to be tilted slightly toward Earth's line of sight, with the black hole itself sitting closer to us and the stellar wake extending away into the distance. That orientation meant the shock-heated gas directly in front of the black hole is moving very slightly toward Earth relative to the rest of the structure, producing a small but measurable blue shift, a compression of light wavelengths toward the blue end of the spectrum that happens whenever something is moving toward an observer. Without that specific viewing angle, the velocity signature the team needed to confirm a supersonic bow shock might have been effectively invisible, folded into the noise of an otherwise ambiguous, hard-to-interpret smudge of light. In a very real sense, astronomers got lucky with the angle nature happened to hand them, and it's worth acknowledging that luck rather than treating this confirmation as an inevitability once JWST turned its instruments toward the right patch of sky. There's also a broader demographic puzzle in astrophysics that a confirmed runaway black hole population could eventually help resolve, and it's one worth understanding because it connects RBH1 to questions astronomers have been quietly wrestling with for years. surveys of galaxies across the universe have occasionally turned up systems with oddly underweight central black holes, ones that seem smaller than what the standard relationships between galaxy mass and central black hole mass would predict, alongside scattered, diffuse patches of star formation sitting unusually far from any obvious galactic disk or nucleus, the kind of loose, disconnected stellar populations that don't fit neatly into standard models of how galaxies build their stars over cosmic time. If runaway supermassive black hole ejections turn out to be a genuinely common byproduct of galaxy mergers across cosmic history, rather than the rare, one-off Curiosity RBH1 might currently seem to represent, both of those puzzles could have the same underlying explanation. A galaxy that loses its central black hole to a gravitational wave recoil kick would naturally end up underweight relative to expectations, and the trail of star formation that black hole leaves behind as it exits could plausibly account for at least some of the scattered orphaned pockets of stars that don't sit within any obvious host structure. None of that is confirmed yet. It remains a genuinely open hypothesis rather than settled science, but it's exactly the kind of connective thread that makes a single confirmed detection like RBH1 valuable well beyond the specific object itself. It gives researchers a real physically grounded template to test against these broader unexplained patterns, rather than relying purely on theoretical modeling with no direct observational anchor. What RBH1 ultimately represents is a genuine shift in how astronomers think about the permanence of supermassive black holes within their host galaxies. For most of the history of extragalactic astronomy, the working assumption was that these objects, once settled at a galaxy's center, essentially stay there for the rest of that galaxy's existence, anchoring points around which everything else orbits and evolves. RBH1 is direct, confirmed proof that this assumption doesn't always hold. Under the right violent circumstances, a merger between two galaxies, an asymmetric burst of gravitational waves at the exact moment their central black holes finally combine, a 10 million solar mass object can be flung entirely out of the only home it's ever had, sent hurtling through the emptiness between galaxies for billions of years, dragging behind it, almost as an afterthought, a 200,000 light-year trail of brand new stars that would never have existed at all if that violent ejection hadn't happened in the first place. It's a strange kind of cosmic consolation prize, destruction and creation braided together across an unimaginable scale of space and time. And it's very likely just the first confirmed example of something that's been happening quietly across the universe for billions of years, waiting for the right telescope, the right team, and the right stroke of observational luck to finally catch one in the act. That last point is worth sitting with for a moment before we close out. Science doesn't usually announce its biggest discoveries with fanfare. This one started as a faint, easily dismissible smudge in an image nobody was specifically looking for, the kind of thing a less careful team might have written off as a detector glitch and moved past without a second glance. It took years of patient, methodical work, ruling out the boring explanations one at a time, gathering better data from 3 different observatories, and being genuinely willing to follow the evidence toward an answer stranger than anyone initially expected, to turn that faint smudge into confirmed proof of one of astrophysics' oldest theoretical predictions. That's usually how the biggest discoveries actually happen, not with a dramatic flash, but with a strange little anomaly that nobody could quite explain, and a team stubborn enough to keep asking why.